Today, okay, so this call is being recorded. Today is April 15th, 2023, 12:07 Pacific time, or whatever time you want to use. So we're going to,
It's 1900 hours UTC.
That's correct.
there you go, the official. So we have Adrian Marsh here at the shop here in Spokane. We have Eric. I'm here. It's been a pretty busy last couple of weeks. We've made a lot of progress. So we'll just kind of go through this call first, get updates from everybody, and then on my mobile phone, I'll walk around and kind of give a little tour of all the stuff that we've been working on. We're well ahead of schedule, and still waiting on some parts to come into the mail to wrap up a few things. But let's see. So I want to mention that we have the conference coming up, Energy Science and Technology Conference. It'll be the 12th annual event. It'll be here in Spokane, Washington, right here at my shop. And the official website for that is energyscienceconference.com. And then if you go to the main menu bar, there's a 2023. Actually, let me just pull it up here real quick. In the main menu bar, if you click on the 2023 conference schedule, and the schedule is pretty much about 95% locked in. You can look at all the presenter bios, the talk descriptions. It's 5 days from July 5th through the 9th, and which is a Wednesday through a Sunday. And you can look at all the presentations. I think there's probably about maybe 16, maybe 17 presenters, and there's about 21 different presentations. So it's going to be a busy 5 days. And then for tickets, if you're on the homepage of energyscienceconference.com and you scroll down, there's only about 27 in-person seats left. This is going to sell out. We limited it to 65, so the shop's going to be packed here. And then we also have streaming tickets available. But if you click either this where it says Energy Science and Technology Conference or Get Your Tickets Now, they both these buttons go to the same place. You can click that, and that'll forward you to emediapress.com. And if you scroll down, the button on the left is in-person tickets, and the button on the right is the live streaming tickets. And so Eric is going to be giving 3 presentations. We've kind of already covered this on some of the other calls, but it's on Tesla's 4-phase system. That's going to be a 4-hour presentation. Eric is also going to do a 90-minute presentation on an analysis of one of Bach's pieces using the 4-phase type of analysis method. And then we'll be co-presenting on the audio modulator bay, which is what Adrian and Eric have actually got worked out all the bugs. There's just one more unit that needs to go into it, and we'll kind of take a tour on what's going on there. And then Adrian has a couple presentations. You can see that. So does Griffin, Hakasays, and I'll be doing a couple co-presentations with a few others. EPD Laboratories, I'm going to bring this up real quick. This is Eric's website, ericpdollar.com. So most of these blog posts are done by Griffin, is kind of putting some updates on here. But in the left column, if you scroll all the way down, EPD Laboratories, Inc. is a 501c3 nonprofit corporation in the state of Nevada, and it solely survives on donations. And when you scroll down far enough, there is a address where people can write checks or money orders made to EPD Laboratories, Inc., send them to me in Spokane, and then I just sign those and send them down to the bank in Nevada that pays the bills, that buys parts to work on some of these projects. There's also a PayPal link, and this is how most people donate. And there's an option to do a recurring donation. So even if it's $5, $10 a month, and that's just automatic every month, that's what helps out and makes a lot of this possible. Eric and Adrian are here for about another 2 weeks. They're both taking off at the end of the month. Eric, do you want to go into kick it off by going into anything regarding your presentation or anything going on here, and then we'll do a walk around with the phone at a little bit later when we actually walk around and show everybody what's going on.
Yeah, I think you kind of basically pretty much said what the presentations are about. At this point, there's no point in going into lengthy description, being that we're focused on what we've been working on. So I'm pretty much just in the answering question modes right now for the most part.
Okay. And then Griffin, I think you had a slideshow, right?
Yes, I do. I believe Jeremy has one as well.
Okay, and then Griffin's website real quick is griffingBrock.com. Let me just show that real quick, and then I'll enable your screen sharing. Okay, let's see here. So this is Griffin's website, griffingBrock.com. He also has a donate button. These donations go to experiments. You know, you can follow Griffin through his website on the projects he's working on, and you can see that the money is absolutely getting put to good use. And so that's griffingBrock.com.
So this is essentially a small update of what I've been working on, and I'm sure afterwards Hakasays will elaborate on his personal endeavors as well. At the present, as well as with a multitude of other projects, I've been concentrating on the replication of some of Nikola Tesla's original oscillators, specifically this design, which was showcased in the latter half of the 1890s and presented at his New York lecture. Now, what makes this oscillator rather unique is that by no means is it a conventional Tesla coil, so to speak. It does not have a typical spark gap or a make and break timing as associated with conventional units. And one of the main or the two aspects of its importance is that it's able to achieve fairly high frequency and high potential. Of course, these frequencies are considerably lower by modern standards in the couple hundred kilocycle range, but nonetheless, it's probably adequate for some very interesting shadow graph and radiant tube research, as well as with other high vacuum experiments that relate to this oscillator. Now, the construction of this replication initiated with the design and the original description of this apparatus, which does not really seem to be that present. Tesla did not extensively write on its design other than a couple drawings. The one shown before is an example of the schematic. It's a very simplistic design. We could see that there is a large coil or large drum, which is labeled L. It's slightly cut off on the screen, possibly. And it essentially acts as a charging coil in that it acts as a series inductance in series connection with the feed line that's typically connected to the common AC main system as Tesla employed. And it also actuates the spark gap, which in a electromechanical sense opens and closes the gap in relation to the 60 cycle line. And of course, this is fed into the primary of the transformer, which is encased in wax, and the secondary likewise. But of course, the secondary, which comprises two oppositely wound pancake coils of multiple layers, makes for a very unique design, which has not really seen replication or in-depth analysis since the 1890s. That's one of the main driving factors behind this replication. So, of course, the secondary coils, both of them are encased in a tubular form with a paraffin wax. It is a very messy construction, but nonetheless, it was quite successful. I believe I showed this picture in a previous live call. And of course, this entire drum is then encased in a outer layer wrapping with, of course, the primary windings affixed on its surface. And Tesla considers that the primary must be made over the middle connection of the secondary coils, as the potential is low at that point, also due to a phase disalignment in the overall setup of it, so that it makes it advantageous so that any arcing or stray discharges will not ruin the relationship between the secondary and the primary configurations. And this charging coil, which is not the secondary coil, this is what was shown in the first photograph, essentially is a very large inductance coil with multiple taps as shown at the base of the coil, affixed by brass posts. And we could see that there exists at the top of the charging coil a spark gap which acts electromechanically. And of course, the brass fittings, which were graciously machined for me by Hakasays, which of course I wouldn't have been able to accomplish, are affixed to the top of the coil. And keeping in mind, since Tesla did not give full-on detail of this apparatus, this oscillator, I had to rely upon a specific image, which was shown at the front or the beginning of this slideshow, in which he does give some very rudimentary descriptions in terms of size. And using proportions and rudimentary calculations, I have been able to formulate an approximate dimension and dimensions of different parts on this apparatus. So this is the charging coil, and this is the rudimentary setup of the apparatus. Obviously, in this picture, we see that a majority of the hardware is missing, but nonetheless, this is the preliminary outline of the oscillator. And we could see the large drum secondary is located in the back and the charging coil in the front. And the base upon which the setup is affixed, we could see the two connecting binding posts that connect to the mainline supply, as well as the two canister or screw-on fuses which Tesla employed in his original oscillators. And of course, this is the completed replica, showcasing all the brass and hardware, which is the finalized version of the setup. It measures about 12 inches in height, around 7 inches in about diameter, and around 9 inches, I would say, in length. So it makes for a very compact version of a high-frequency oscillator. So because this unit was recently finished within the last couple hours, I have not been able to test it to its fullest just yet. So that will likely proceed within the next day or so. So this is the completed unit, and it will likely be able to produce rather interesting discharges, but also provide adequate supply to certain high-frequency lamps and other research which is sure to come and be presented at this coming conference. Now, of course, with the other projects that are going on, actually, I forgot this picture. This is the other side of the unit. We can see the other connections connecting to the primary binding posts. And of course, for a comparison shot, let's see, I move this to the side, we could see that it's a side-by-side image of the oscillator and that of Tesla's original oscillator from 1897, I believe. That's around the rough year that it was created. So that just gives a reference of what it originally looked like. Of course, there are some irregularities and not a perfect replication, as Tesla did not give full-on detail. Now, going back to the other projects which have been underway, let's see. There we go. This includes the seismic forecasting rack and unit, which Eric has been assisting me in its construction. It's an experimental setup. It essentially comprises two panels for now, which the middle section, incorporating the two pilot lights, consists of the actual vacuum tube amplifier. Now, this amplifier, mind you, is not a conventional cathode follower unit, but rather a radically new design which Eric has been able to create and I am experimenting with at the present. Now, of course, the search and analysis of this unit makes use of some specialty equipment, which at the moment needs immediate attention and servicing, as further analysis cannot go on without these instruments being, I guess, operated correctly. And above the rack, or above the panel, above the pilot light section, that comprises the repeating coils and some other experimental units which are attached and fixed to the back of the panel. And the other sections on the rack are irrespective to the amplifier, but do operate and do pertain to other sections of the seismic rack. And to keep pictures short, this is just the front view of the rack itself. And to go into other projects involving the shadowgraph and radiant matter experiments, I have developed a new tube, which is unlike the other balloon type or 3S envelope type vacuum tubes, which comprise the Tesla single electrode element, that the question and the quest for directional beam, or I guess focusing of the rays, or particles or what have you, which is still being investigated, I have developed a new design which comprises a larger, or I guess blown out section at the end of a skinnier elongated tube. And in theory, this is so that to concentrate the plasma and other actions emanating off the electrode and project themselves forth onto the outer wall, the inner wall of the glass at the very end of the left-hand side of the tube. Now, of course, comprising theory and actual experimental practicality, theory and my hypotheses were correct in that this tube design did in fact concentrate the rays heavily, and the attenuation of the rays broadside to the tube and backside to the tube were heavily reduced so that the projections and the ray intensity was maximized at the front of the tube. Now, what was interesting upon observing the action of this prototype is that because of the concentration of the plasma and the rays emanating from the electrode, there is a very unusual uneven phosphorescence which occurs on the inside of the bulb. And this indicates that the rays are indeed being compacted and that the actual diameter of this phosphorescence, which is represented in this picture, which we could see as the circular blue circular hue, correlates to the diameter of the actual elongated tube, which is shown in this picture. So that creates a very interesting observation in the sense that the rays being projected do not have time to expand themselves to a larger diameter as with the other pear-shaped tubes, but are rather concentrated as a very defined spot about 1 inch in diameter. And this also creates a very uneven heat distribution. Now, I won't get into it any further as I will be presenting this as well as some other research, which is quite astounding, at the next conference in my presentation, as well as the laboratory results from a lab analysis, which was able to conduct very rigorous experimental metallurgical analysis on the electrodes of these lamps. And it is interesting to which the compounds and the, unearthly metal conjugates, which have somehow manifested themselves on the surface of the electrode, have been able to been developed through the process of actuating these type of lamps. So I will be getting into that in quite in depth in my next presentation. And that pretty much concludes the projects being conducted thus far. I guess we could hand it over to Hakasays.
Do you have a website?
Hakasays.com/blog, but I haven't updated in a while. Really, Griffin and Eric's work will be more bang for your buck.
Okay.
So I've had the problem lately of you either have, time, money, and space. And this part of life, I've had everything but time. So life intruding and things like that. So now that we're getting fairly close to the conference, I started focusing on one of the experiments I had started some years back, which was the John Trump rotary electrostatic motor, partly because I already have a couple failed attempts at construction and a lot of lessons learned, and partly because of the work with Adrian and Eric with the audio modulator bay that may end up being a compatible system for it. So going with that, this is one of the old photographs from John Trump's era. You can see the actual rotor. You can see the stator that's on here and compare it to what Chris Carson's prototype was earlier. You notice that it's much larger and much fewer plates. If you zoom in, you can see there's only, looks like 4 stator plates on here, which would mean 3 rotor plates. The RPM is unknown, but based on the bearings, it wouldn't be more than 15,000 RPM. But the main reason why these motors performed very well in his experiments were because they were under a vacuum. As Eric would say, or he would know that the higher the voltage you get, there is an exponential compounding of the power output, whether you're using it as a motor or a generator. So here's another pic from the era demonstrating one of the motors that Trump had made. Notice it was, I think that's probably somewhere around 7 to 12 inch diameter. And notice the entire assembly, there's only 4 plates. 3 rotors, and the entire assembly goes inside a high vacuum chamber. And the vacuum chamber is what allows you to reach the extremely high voltage, the extremely high voltage being what results in the extremely high power capacities. So the system that I was going to work on here, I wanted to focus on getting a electrostatic converter that can be operated inside a vacuum. So I spent some time on the CAD, got a model banged up, had a water jet cutting shop make a big batch of these. These are 8-inch stators, or sorry, 9-inch stator with an 8-inch rotor. It's built on a 5/8 shaft. I have about, I have extra, but the planned motor is going to be 12 to 13 blades per system. So been kind of busy, but I found some time to start piecing things together. This was part of the first rotor, part of the stator stack that I've been working on. They're approximately almost 3/4 inch spacing, but that turns out to be closer to 3/8 plate spacing. Long story short, the math is very ballpark, especially since it's unknown what type of voltages we'll be able to accumulate with this. But the likely aspect is we'll probably be able to get at least 50 to 100,000 volts, which means a motor of this size may be able to reach up into the kilowatt range if we can get it up to a good RPM. So here's just some more of the relative progress that's been on. This is not aligned, obviously, but the main part is machining the bearings, machining the spacers, machining all the brackets and things to put the thing together. As you can see, a lot of that's done on the CNC, but you still have to do CAD, you still have to do speeds and feeds, and take a lot of time putting things together. These bearing block assemblies, part of the motor, just got finished yesterday. Finished up on the lathe. Probably a few weeks out before I'll start having something that I can actually start spinning up and putting in a vacuum, but progress is getting made, slow but steady. The only other thing is one of my early experiments, rotary static converter, was using a 4-inch version before I had good access to Chris Carson's prototype. And that motor, the blade spacing was far too short, so the rotor couldn't be spun up more than a couple hundred RPM for fear of shrapnel blowing across the room. So basically, I took all the prototype, disassembled everything, and redesigning with more appropriate spacing, and being a much smaller rotor, much smaller motor with almost all the parts. It's a simple side project. So hopefully we'll have 2 motors to actually show off on this, and as long as we get one of them going good, then at any rate, we'll have some interesting results to compare and see what the performances are. Only other thing I had was a very extremely crude rudimentary test was I do have a vacuum chamber and a fairly decent 2-stage rotary vane pump. So I did a rudimentary foil experiment by putting about 50 kV across a couple pieces of foil, pumping it down to a deep vacuum, and trying to confirm what the characteristics and corona discharge, see if there are any hot spots, and generally get an idea of what the electrostatic motor is going to look like when it's spun up under a high vacuum. So like I said, not a lot finished right now, but progress, slow and steady, and hopefully work doesn't intrude too much. So with that, I'll pass it back to Aaron, or who's next?
Yeah. Let's see. I just want to show a presentation here that's relevant to that.
I should have mentioned that. Yeah,
you're right there.
Your previous year's presentation on the Chris Carson motor, and actually anything with Chris Carson on the late 90s, early 2000s presentation with Eric does a fairly good job. As well, the John G. Trump, I believe, the MIT physicist that was working with Van de Graaff and a few other people that actually prototyped this. You'll find a bunch of patents and research papers online if you want to look up any more detail. Otherwise, we'll have something to show off in July, hopefully.
Okay. That's right. Here, just give me a second. Yeah, so this is a presentation that Eric and I co-presented on. Eric did it over the phone long distance since he wasn't able to come up in person. But this kind of goes over all the basics. There's a couple video clips from John G. Trump, patent references, titles of papers that he wrote. And so this is kind of the good basic intro to this whole rotary electrostatic generator.
And I guess I could add one more thing, which is the more novel aspects of this, aside from being a motor generator that has no use of magnets whatsoever, that has no coils whatsoever, operates without any of that, is that it has a potential to demonstrate something that Eric has gone over in previous presentations, which was on parametric variation of capacitance and how you could conceivably get non-linearities when operating these motors in the proper configuration. So that'll be interesting.
Okay. We have Dr. Adrian Marsh on the line here on the other side of the shop. Hopefully we don't get any feedback, but do you want to announce anything and share your website?
Yes, I'll give an update on what we've been doing here as well. Aaron, just you don't need to give me a screen share. Do you want to just bring my website up just to?
Yeah, I'll do that.
Show?
Here's Adrian's website, am-innovations.com.
Okay, great. Thanks, Aaron. Okay, since the last live call, I've really been focusing on the preparation for being here with Eric and with Aaron. Okay, so we went through all of the wiring, checked everything right from the AC inputs onto all of the panels. We took almost all of the panels out, fired them up individually, fixed any wiring faults that we found, and that led us to a point where we had the power amplifier was working. We made a temporary matching system to the Hewlett-Packard oscillator, which produces just enough output to drive the power through the power stage through a matching transformer. So we were able to then run it properly using the high voltage supply. That's nominally in the region of about 2,800 volts. We round it up slowly with a variac. It's always a good idea to do these things progressively in stages. We didn't really have any problem other than the fact that we discovered that there was a slight ticking. So a slight voltage ticking on the high voltage output transformer. So the modulation transformer as the last stage, which did worry us for a while because that might indicate a broken down winding. We took the transformer out and tested it against another transformer. But it turned out in the end that it was two components slightly too close on the divider network, which then feeds to the oscilloscope. So there are two outputs that are taken off of the modulation transformer. These allow you to monitor the output of the overall audio-based system. And two of those components, there was a capacitor and resistor there in the chain, which is a little bit too close. Not actually touching, but close enough with the high voltage, and that was causing the ticking. So fortunately, nothing wrong with the transformer. Those transformers are almost impossible to find now, and if you can, they're very expensive. So then we put all that back in, and we had a successful test. Probably Aaron will show some pictures at some stage. We took a little bit of video and some pictures. So when that's downloaded, that'll be for everyone to see. And we are now just waiting for two replacement 1625 tubes in the exciter unit, which will go in between the Hewlett-Packard oscillator and the power amplifier. That will go back in next week, and then the entire rack is completed, which is it's exciting. At the same time as that, I've been upgrading. Last year, I used an apparatus built by AM Innovations for the golden ratio discharge. One of the presentations that I'm going to be giving at the conference this year is a much deeper dive into the golden ratio discharge, and I'm going to be using a different generator unit. I'm going to be using a GU5B Russian power triode generator, which has a more flexible frequency range and also is able to develop quite a bit more power. Although it's specified to a maximum plate voltage of 5 kilovolts, I've successfully run it up to 9 kilovolts for sustained periods of time, and that actually makes the discharge considerably larger. So I will be bringing that from my lab in the UK, but I also needed to upgrade the high voltage power supply that I have here, which is currently a 4 kilovolt, 2 kilowatt unit. I'm in the process of upgrading that to an 8 kilovolt, 2.5 kilowatt unit. So that will provide all of the input power and the high voltage for the GU5B generator. And that will allow me to power a range of coils during the demonstration and for that presentation. Now, at the same time, Eric and I were looking at plans for the RF rack, the RF bay that we have here, because part of the one of the demonstrations at the next conference will be for a much higher power flame speaker. At the moment, we've been using the Collins at 100 watts, but the overall plan, of course, is to get up to 1 kilowatt. There is still a lot of work to be completed on the RF bay. So what we decided to do is we will combine my generator that I use for the golden ratio discharge, because that basically is a configurable generator that can run in push-pull mode. At the moment is currently I'm running it as an oscillator, but it has all the patch boards on it to allow it to be wired to perform high power amplification at the RF stage. So that means that we would be able to combine the high voltage supply that's currently installed in the RF bay and use that to power the AM Innovations generator. That's a pair of 3 500ZG tubes. It's good to about almost 2 kilowatts, and it's completely fully developed and tested. So we can make a hybrid unit in the RF bay. We'll use that generator plus the high voltage supply, and that still needs to be looked at. I'll be working on the high voltage supply in the RF bay this week. And if all that goes well, then we combine those two units and we should be able to drive, we'll have the audio bay completed, and we should be able to drive the flame speaker, I would have thought, at least to 750, 800 watts, maybe more than that. Let's see how we go. So that's work in progress. We're also looking at the Colorado Springs experiments. We need to modify the second coil. The original coil was modified in 2019 during the conference. We need to upgrade the other coil to rewind it. And then we will be able to do some single wire experiments. I think we're planning to demonstrate that also at the conference. And we will use the hybrid RF bay, and we will use the audio bay, completed audio bay, to do those experiments. And then the plan is, after the conference, the necessary work can be completed on the RF bay. So the generator, my 3500ZG generator, will come out. That will obviously remain here at the shop for other useful demonstrations. And then the RF bay will be completed, which is a fair bit of wiring, documentation. We've been making circuit diagrams as we go along. And Eric has also got a lot of notes and diagrams that he's going to work on Tonopah. So I would hope that towards the end of this year, we would have a completed audio bay, RF bay, with the accompanying schematics, circuit diagrams, and any documentation, which would obviously be a major milestone. I think we will all be very happy, Aaron, when we get to the stage that those two are fully functional. Otherwise, we are doing small things in the shop as well. I have a real interest. I've always had a real interest in test equipment. So we've been going through some of the test equipment here, working out what's working, doing a few repairs. Eric's been working quite hard on the vacuum tube oscillators that we have here, both the audio and the RF oscillator. And I've been working on some of the Tektronix and Hewlett-Packard equipment here. We also have fired up a Navy Tektronix, so a Navy specification Tektronix oscilloscope here, which is helping Eric a lot. That's fully working now. And we have also invested, Aaron has invested into some quite high specification test equipment. So we now have a 7 kilovolts Hewlett-Packard differential probe, which is that's a really nice piece of equipment to have, because it means we can attach any of the high voltage work that we're doing directly to test equipment without it damaging the equipment. So at that level, about 7 kilovolts, it will take up to 10 kilovolts without a problem. That allows us to attach it to everything that we're working here, and we can look at the waveforms, and it will go up to about 50 megacycles, that probe. So that's good to have. We also just arrived, we have a Tektronix current probe as well. That's 50 plus or minus 50 amp up to 15 megacycles. It's the same equipment as I'm using in my laboratory in the UK. I did show that equipment on the last live call, which I'm using to measure directly the generator and directly into the Tesla transformers that I'm using for the golden ratio and for other experiments as well. So given that we're only halfway through, Eric and I being here halfway through April, we have already accomplished a great deal, and I think we're going to accomplish a lot in the 2 weeks that we've still got to go. Hopefully, we can get the hybrid unit working, which means that we would have a powerful flame speaker demonstration for the conference, and also other related experiments with the cosmic induction generator tubes. Just on those coils for a moment, we've done a comprehensive vector network analysis now of the cosmic induction generator setup. So with all the coil arrangements, so with the voltage coils and the current coils individually and all combined together. So we have a very interesting picture now of how that looks both in impedance and admittance across the frequency bands of interest. That's also something that Eric and I are investigating in a great deal of detail, is this second mode that we have in a Tesla transformer. There's been a lot of talk and exploration that we've looked into that. It is a very unusual mode. I mean, we've so far called it the parallel mode, the series and the parallel mode of the Tesla transformer. And some of the things that we're working on now, that parallel mode is very interesting because it is another valid mode of the Tesla transformer. It's obviously easily suppressed because it's very high impedance. That's why it's called the parallel mode. Tesla transformer has a very strong parallel to a crystal resonator, which also both has a series and a parallel mode. And that mode always, the parallel mode in the Tesla transformer always passes through 0 degrees phase. And that makes it very interesting. And in actual fact, the golden ratio discharge is the product of actually running that system generator at that parallel mode, which is also unusual. So we're looking both theoretically and experimentally into that. We'll have much more on that to share in subsequent live calls, and there will definitely be more in the conference. I will be going into that in more detail. The one thing that it does enable, running at that parallel mode with a self-oscillating system, is a great advantage when studying the natural principles in nature. I mean, like the golden ratio discharge and fractal discharges, because you are allowing the Tesla transformer or the transmission line, or however you choose to look at the system, you're allowing it to resonate freely at its own spectrum of frequencies, and that includes harmonics. And that is quite an important underlying principle if you want to work with things like the golden ratio discharge, is rather than the generator forcing the coil or driving the coil, if you like, at specific frequency, you are allowing the Tesla transformer to adapt to the drive conditions. So the generator ends up supplying the high voltage and the high frequency necessary, and the coil is self-resonating at its own spectral bandwidth. And we're going to be going into that in more detail at the conference as well. Eric, did you want to say more about what we were exploring with the series and parallel modes, or anything you wanted to add extra to that?
Yeah, I got a little bit to add.
Okay. Yeah,
so the series mode's kind of easy because one end's just neutral. But the parallel mode's a little more difficult because if you ground the neutral, it disappears. So this opens up a whole new avenue with respect to the output admittance of the coil, the spark or the light bulb or whatever. What is the input impedance necessary for the other side of the coil, being now that you cannot ground the neutral and expect it to exhibit that mode? In fact, Griffin and I Griffin did the experiments. I just kind of set it up, but the parallel mode was completely suppressed when the neutral of the coil was solidly grounded. So that opens up a whole new level of experiments. Is that input impedance inductive, resonating through the transfer impedance of the coil to the output capacitance, or should it be capacitance fed? So now we just opened up a whole nother avenue that has to be explored, which is now, concatenated with along all the rest of it. So things are kind of spiraling into another level of complexity here, and trying to keep all this stuff together in my head. If I don't have a nervous breakdown by the end of this episode, it'll be an absolute miracle.
Well, I mean, at least we're having fun though.
Well, we're having fun. Yeah, we're having fun.
I do have a quick question. The audio modulator bay, what was the voltage and power rating you were expecting on that?
It's 750 watts at 2,400 volts.
Okay.
That's the rating of the tubes. So I expect a kilowatt. If it's going to run Class C, a kilowatt would be easy. So you have to remember, the thing also is an ultra low frequency transmitter for driving Alexanderson antennas. Not that that'll ever happen in this neighborhood, but it does have that level of adaptability. It's quite powerful.
Okay, because it could also be used to adapt with the electrostatic converter, as long as we match the impedance.
Yeah. So the electrostatic machine, at some point, it's going to have to go 4-phase, because if it's 2-phase, or what people erroneously call single phase, it'll have zero starting torque as a motor, and it'll have to be brought up to synchronous and let go. But it'll have to be 4-phase at some point. But spinning the thing up and building a network to go between the modulator bay to step the voltage from 2,400 up to about 100,000, there'll have to be a constant potential, constant current network, or quarter wave line, or analog computer, or whatever you want to call it, to generate the 100,000 volts. Then the electrostatic machine will connect to that, and then there'll be a small little DC motor that brings the electrostatic machine up to speed so it can lock in to the frequency, and then whatever DC motor is doing that will then become a generator, and then you can start to actually put a load on it and measure its power. That's the plan. And then once all that's developed, then a 4-phase machine needs to be constructed, and this whole thing needs to be done down to Tonopah at a level of probably damn close to 9 kilowatts. 4-phase at 7,500 volts per phase, and that's when like a 10 or 15 horsepower machine can be finally presented. So I already have the 3-phase power at the building. It needs to be distributed and connected. The 5 kilowatt AM transmitters are already installed. Each one has at least a 3,000 watt modulator. Each one uses a pair of 4-1000A tetrodes, which is a rather beefy tube, and then has an oil-filled output transformer that delivers a maximum RMS voltage of 7,500. So I expect 4 kilowatts, not much problem, and possibly even more, because the transformers are very large and they're oil filled, which is important but rare in modulation transformers.
And that will be one that you stand well back when you turn it on for the first time.
That will be serious. It'll be a big machine.
Yeah, indeed.
And probably, well, I don't know how long it'll take to get to that point of vacuum and everything, but at least without the vacuum, it can partially be demonstrated. I don't know. That's a big undertaking to get to that point.
Yeah, what we really need is a couple prototypes to get a feel for what type of vacuum is required, what speeds and feeds and things like that. And then turning to 3-phase and 4-phase is almost trivial, because all you have to do is separate different sections of plates and phase adjust the rotor.
Yeah, there'll be like a complementary set of plates at right angles to each other.
Mm-hmm.
I think that's kind of already indicated in some of the Trump writings and patents and what have you. I can't, right off the top of my head, I don't know automatically what to do, but it couldn't be that complicated.
Yeah,
So
it's simple mechanical.
It'd be, I already would consider it to be, miraculous if we just got to the point where, something was built here that would run off the existing modulator bay, and demonstrate the motor effect.
Exactly.
That's a long, expensive, tedious project right there. And that modulator bay was a long, expensive, tedious project. And then we had this horrible NAM occur, where this little high voltage ticking was going on, which is usually indicative of an impending blast. And the question was, where was it? And it acted like, it was the modulation transformer. And if we lost that modulation transformer, which was already a gift from Jesus, if that thing got screwed up, that would just be the end of the whole deal. It was a scary thing. And so we went through it, and what it turned out to be, it was in the course of getting bounced around and all that, is on one of the resistor capacitor network terminal boards, one of the components was pushed too close to the other one, and it was making this little tiny sparking. And then we exercised the thing, and the demons disappeared. And now we're at the last step, where the so-called new old stock tubes are all bad, and the China Reich tube sockets, brand new tube sockets, are no good. And we're fighting all that to get the 1625 driver exciter unit going. So I'm performing that exorcism now, and then along with all the other stuff. So presently, at this instant, I'm getting the test oscillator going for the Colorado Springs coil. I'm awaiting the tubes, and Adrian is working on the network rectifier assembly to put the 4,800 volts amplitude modulated power out to his unit. And the objective, by the end of this episode, we should be able to exhibit the flame speaker at 10 times the power or more than we previously have, and that's going to be exciting. So that's it for me.
And Hakasays, just to add to the something Eric said, because you're asking about the audio bay, we tested it last week in the range of about 2,400 to 2,800 volts plates, between about 50 and just over 100 milliamps plate current, depending on. So it should be, provided it has the right matching. I think it should be adequate for.
Yeah, the matching is going to be the big question, and the motor will have to be finished before we find out what kind of voltage rating is required. We'll probably be able to get 50 to 100 kV safely, which will put it well into that range of 750 to a kilowatt.
Okay. Do you have a suitable power supply there, Hakasays, in order to be able to do some initial testing?
I'm going to have to spin it and see what type of characteristics and power we get out of it. I don't have anything to drive it directly other than turbine motor type stuff.
Okay.
I can only use it as a generator.
Okay. Should we can either take questions first or do a tour? What do you think makes sense, Adrian?
I think probably taking questions because we often run out of time for questions.
Okay. So if anybody has any questions under reactions at the bottom of your screen, there should be a if you click on that, that'll be a raising hand little button there, and I can unmute you and you can say what your name is, where you're from, and who your question is addressed to. So if anybody has any questions, go for it. Victor, I know you said that you had I think you're typing some stuff in the chat box, but Victor Sears, let's see if we can get your audio working, and also you can ask Eric when is a good time to actually for you to come to the shop to talk about the math. Trying to find your thing on here. I don't see it. Victor is not on here anymore. Yeah, he is. You there, Victor? Can you hear anything? Never seen it work. Okay.
Can you hear me?
Yeah. Yeah, go for it.
I was asking about how the modes that they were talking about compared to transverse and longitudinal. But if Eric wanted to see the math, and did he bring his synthesizer up with him?
No.
Oh, okay, because I got keyboard equipment. I mean, I can hook my computer up if you wanted to see that BCB rack to build that digital rack he was talking about wanting to do. But I guess we can talk about that later.
Okay.
People have some questions.
So the different modes first of all, the different modes you were talking to, who are you addressing the question to specifically?
Adrian was saying something about
I can add something, Victor, yes, and then perhaps Eric will also have something to add. We have speculated on this. I mean, you know, we are calling these currently the series and parallel mode because of their very close correspondence to a crystal resonator. I mean, with a crystal resonator, I mean, Eric drew a equivalent circuit, which is also equivalent circuit I had in my presentation last year at ESTC, which is really the same as a crystal resonator. And there you have very pronounced series and parallel modes. So because of that similarity, we've called it the series and parallel modes. But there is one major difference, is that the crystal resonator shows it is basically a multi-frequency resonance. So two frequencies with two phase changes. So in other words, the series mode has a phase change, and so does the parallel mode. Also has a significant phase change. That's for a crystal resonator, but that's not the case with the Tesla transformer. So the Tesla transformer has what looks like a series and parallel mode, where the series mode has a significant phase change. So in other words, it changes from being inductive to capacitive, and it goes through a large phase swing. I mean, in an ideal case, it goes through a -90 to +90 phase change. But the parallel mode does not go through that same significant phase change. It's always at 0 degrees phase. So there are differences there, and we have speculated this week that maybe it's possible to consider the series mode as a transverse mode and the parallel mode as a longitudinal. But I think it would be quite early for us to really conclude that that's the case. I mean, it needs some considerable investigation, both theoretically and more in practice. But I mean, practically, you are able to put power into both modes. So in other words, you can run a Tesla transformer generator at both the series mode and at parallel mode with considerable power. So it is not like a phantom mode or something which is an artifact of some kind of measurement. It is a real, and in actual fact, my golden ratio discharge system is actually running specifically at the parallel mode. It is not running at the series mode, and that's with quite a lot of power. I mean, you know, I can put almost 2.5 kilowatts through that Tesla coil on that mode. I mean, you have to arrange your generator so it has a high output impedance, essentially, because I mean, if you try to terminate on a low impedance, as Eric was saying, you're going to collapse that. You're going to suppress and collapse that parallel mode because it's such a high impedance mode. So does series and parallel correspond to transverse and longitudinal, or a mix of those, like a waveguide or a transmission line? That's very much still work in progress. Eric, would you add to what would you add to that?
Well, you pretty much covered it. In the past, I've used the transverse and longitudinal mode. In general, and from a mathematical standpoint, there's 4 modes. There's the one that's called the longitudinal mode. There's one that's called the scalar mode, which allies with the longitudinal mode. And then there's another side to the thing. There's 2 transverse modes, one that runs around the coil clockwise, and the other one that runs around the coil counterclockwise. And it is, so basically that's easy to visualize because it acts like it's going in between the space between the wires. The longitudinal mode is easy to visualize because that's basically going transverse to the wires, or longitudinal with the direction of propagation end to end. And the scalar mode is that part that has no wavelength distribution. And the whole thing operates as an LC circuit. But that's what I would say that your parallel resonant mode was. But when you said that you found a quarter wave distribution on the coil in that mode, then that's no longer valid. So there's a lot of stuff that needs to be aligned up here. And it's from the theoretical standpoint, you know, and trying to get the overall geometry. And it's going to take a lot of experimenting and fooling around, and it just kind of creates a whole nother, you know, you get more and more spread out, and then you don't get anything done. So it's almost like, you know, this is the point at which another person with Adrian and or my abilities in this has to come in. But we could conceivably be the only 2 people left alive to do this. So I don't know, that's where we're at. Obviously, we can't just keep spreading out here. We got to make sure that you know, at the end of the episode, you know, the flame and the music gets done. You know, it's like a friend of mine, phone company guys say, no dial tone, you don't get paid. So that comes first. Everything else is secondary.
And in a few minutes, we'll fire up the demo. If you were at last year's conference, or if you have a copy of Adrian's presentation from last year, you've seen the golden ratio discharge, but we'll fire it up live here in just a couple of minutes. And I'll take my phone camera over there so you can see it. Adrian has done some modifications on his equipment over there. So we'll show you what that looks like. Eric, when is a good time for Victor to stop by the shop one of these days to chat with you on some of the math stuff?
You mean here, this location?
Yes.
Well, maybe after we got something done. Right now, you know, because we've been doing all this talking on the internet and waiting for parts, and we're already halfway through the month. We got to get down to business for, you know, when we get one thing done, then yeah, so maybe like 5 days, a week, maybe next, not the upcoming week, but maybe the week after that would probably be good. Or you know, maybe even, you know, after Adrian leaves, because, you know, my schedule's more flexible, I can continue to stay here.
Mm-hmm.
Yeah, we've got to put the priority on getting that hybrid unit finished first, Eric.
Yeah.
That's got to be the number one, I think, because that solves all the things that we want to do in one go.
Yeah, that's the fastest route to take to get the musical flame going to, you know, more glorious level.
Okay. And then I see that Bruce Gavin is on the call. And Bruce, if there's anything that you want to contribute, just unmute yourself and jump in. So I'll go ahead and take a question from Mark Udian. I'm gonna go ahead and unmute yourself and then
Hello, can you hear me?
yes.
Hi, thank you. Thank you for having me on. It's great to be here. I would like to ask Eric Dollar a question. First of all, it's an honor to get to ask you a question, sir. It's an electrical engineering situation. What I'm thinking of is if I have a generator, but I run it as an async mode. So then when I put I can hook up a variable frequency drive then I can control how much power I can get out of it by changing the phase delay, correct?
I'm not getting all the words. Some words I'm missing. Did you get the whole thing, Aaron?
No, I didn't either.
Oh my God! Can you hear me? Can you hear me better now?
Well, I can hear you, but the thing is you have an accent that I have a problem with accents and maybe 2 out of 5 words I don't know, I can't make them out, so I don't know what to do.
I apologize. I'm just a little too nervous. I'm sorry. Let's say I have a generator. It's an asynchronous generator. So I have it's an induction motor that is being driven. And let's say it puts out something like 300 hertz. And I want to turn that 300 hertz frequency into 50 hertz frequency to go on the power line. But I don't want to use any electronics. So my question is, if I put a variable frequency drive on the motor and I feed it the frequency at which it turns, then the phase delay will allow me to control how much power I'm getting out of the generator, correct?
Something doesn't sound right there. I can't, I'd have to see a diagram of what you're doing. There's a thing where you connect one motor to another to step down the frequency. It's called concatenation, but that's kind of a difficult process. So basically you have a series of motors that not only, transform voltage and what have you, but they also transform frequency. Steinmetz covers that in his AC book. But basically, you can't just change frequencies in the middle of the stream, so to speak. I don't think it's going to work out.
But what if I change? What if I pulse the phase delay angle? Which
I don't know what any of that is. I don't have any diagrams. I don't have any equations. I don't know phase delay angle. What?
Let me get further. Let's say I can pulse power into a primary of a transformer at a certain frequency. Will the secondary have receive the EMF at the frequency that the power is pulsing at?
Well, then you're using saturable reality. I think actually, it's cut right now.
I
don't want to do that because we're really tight for time.
I could add something just quickly, Eric, as well. Classically, it's quite difficult to take an induction motor that's designed to run at a particular frequency and actually change that frequency because the frequency is built into the design of the induction motor. It might be better off to work with an induction motor which is more closely matched to the frequency that you actually want to drive at.
Yeah, I think he's asking if basically a 300 cycle motor ran at a certain RPM. If it was run at a lower RPM, would that result in a different frequency?
No, it wouldn't.
No.
I think that's the question. I think that's the question, right?
Yeah, but it wouldn't.
The question is if I pulse power through a transformer. Let's say my signal comes in at 100 hertz, but I pulse the power, not the signal. I pulse the power in the transformer. Would the secondary have the same signal as the power is pulsing at?
Well, you would modulate the whatever frequency there is with the pulse and get a whole set of
Right.
sidebands, and you would just end
Yes.
up making a giant mess.
Okay,
Basically, if you're pulsing, you're not creating an individual sine wave. You're creating these jagged up and down. And when you do
But
the
if I
pulse, you're going to
pulse-
get a bunch of harmonics.
but
The
pulse,
thing is, I kind of want to drop this subject. We're not getting anywhere.
thank you,
You
sir.
know, okay.
Thank you.
Okay, go ahead, Justin.
Oh, hi. Yep. I'm Justin, mechanical engineer, graduating in the spring here. I purchased a lot of Eric's work through eMedia Press, so I hope you're getting some of that money kicked back to you, Aaron. My question to you, Aaron, would be, could you define a dimension?
Sounds like that one's for you, Aaron.
Oh, sorry. I meant Eric. Sorry.
The dimension is, you have the dimension of space, you have the dimension of time, you have the dimension of weight, you have the dimension of flux, you have the dimension of whatever. Those are dimensions.
Okay.
Whatever it is you're working with.
Okay.
So
Yesterday I
basically, that's why 3 dimensions of space is meaningless, because there's only 1 dimension of space.
Right.
Those are coordinate systems. The coordinate systems are applied to the dimensions. Mass is a dimension, all those things. Those are your dimensions.
Okay. And I guess to get a better foothold of your content, I've been reading some of Kennelly Arthur's books.
Arthur Kennelly.
Oh, Arthur Kennelly, yeah. What are your thoughts on him?
He's the guy. Him and Steinmetz are the ones that laid all the groundwork.
Okay.
They were
Yeah.
the ones that brought Heaviside into the real world.
Okay. Yeah, especially Algebra Made Easy. That was a really easily digestible book starting out. My other question would be, would you, especially reading Nick Tomic's book, Counter Space, would you think that space is a projection of counter space?
I can't. I don't want to get into defining things that are kind of vague. So
Sure. But would you think like projective geometry might be a good field to study to get a better foothold of counter space?
well, I would believe so. It always seems to be associated with it. Steinmetz had his idea. Rudolf Steiner was heavy into his own form of that. And for me, I just basically keep the thing simple that, space has a complementary component or coordinate system, almost like another dimension, in that, counter space is the space between the lines on the ruler, or the space between the plates of a capacitor. So the more you divide that space up, then the more capacitance you get, or et cetera. And there's something that's growing in a different direction. It kind of ties in with the Pythagorean lambdoma, where one side is 1 divided by 1, 1 divided by 2, 1 divided by 3, 1 divided by 4, and the other side is 1, 2, 3, 4, and so on up the line. So those are the 2 aspects. So basically, an inductance coil encloses space, but the capacitor kind of confines it and draws it together. That's why they're the opposite. And the more plates you have in a given, 1 foot section of variable capacitor, the more capacitance you have. So the space appears in the denominator rather than the numerator. So that's why I call it counter space. Counter space is in the dimensions of 1/centimeter.
Okay. Because yesterday you said that space and counter space are in different coordinates, but are they still part of the dimension of space?
Yeah, they're both in the dimension of space.
Okay. All right. That makes
Yeah.
that a little bit. So when an object like electricity exists in space and counter space, that gives rise to like strains, which we can then see stresses. Is that
Yeah, you can just take it from there, because the dielectric field lives in counter space and the magnetic field lives in space, and then you can get crazy with it.
Okay. All right.
I'm just trying to keep it simple.
All right. Yeah, I was just trying to get a better foothold. Thank you.
Thanks, Justin.
Yep.
Let's see, James Caffrey.
Yeah, thanks, Aaron. Hi, I'm Jim Caffrey from New Jersey, and my question is for Griffin, if you can hear me.
I could hear you.
All right, good. In your talk, I think it was later on, you showed us an unusually shaped tube, wider at the end and more narrow. And then towards the end of your comments, you said something like, you guys saw that there was some unearthly materials gathering on the electrode or something like that. I was just wondering if you could, enlighten me a little bit on what you meant by the unearthly materials.
Okay, well, I won't get into it or disclose too much because it'll spoil the presentation.
Okay, all right.
But in essence is that this electrode, which in this case is made of aluminum, it could be made of various other metals, and I'll explain why why aluminum is preferable. But nonetheless, when this aluminum is provided with high frequency alternate currents of high potential in a vacuum, a moderately evacuated tube, there is a interesting, what seems to be an observable thermal action or an attack on this aluminum surface. And it is only on the surface projecting forth towards the bulb. It is not on the other side of the electrode. So it's a very directional formation. And it's also quite defined that there's a specific spot of attack. And it came to me one day, as well as discussing with other colleagues of mine, that this thermal attack is creating a layer of some type of matter or substance, which we don't know what is somehow manifesting itself, or I suppose being created, or if you will, transmutated. Now, I won't get into further detail of that, but essentially I sent this sample of an electrode from one of these bulbs to a scientific laboratory up north, and they've been doing some analysis, metallurgical analysis on the sample, and have found some interesting results. That's as much as I'll say.
Okay, well, good. Thanks.
I can make a comment.
Yes.
And what seems to be going on is these projected matter, being that theoretically it would emanate from the nucleus, is some component of the nucleus of the atom is flying off to space, and what's left behind is a different nucleus, which would cause some alternate form of matter. And I don't want to infringe too much on Griffin. So basically that's just kind of what I'm seeing going on here. We've been, hashing this out extensively. And so that's kind of, beta rays are not electrons. Cosmic rays are not electrons. So beta rays do not come from the so-called electron shell of the atom that would just leave the thing charged. Beta rays come from somewhere else. They come from inside the atom. And the notion that Crookes cathode rays and electrons are the same thing is very, very misleading, extremely misleading. And that's what we're going back to the days of Crookes and Röntgen and Tesla and Leonard and all these people, and we're picked up the trail, and we're, it's wide open at this point. Everything has to be re-coordinated back to the original discoveries, and then we're working out from there, and we're basically going to pry the fingers of physicists off of the works of Tesla and Thomson and the rest of them.
Eric, thank you. When Griffin first made the comment, my mind jumped to the concept of perhaps something was being attracted to the electrode. But maybe it's, as you say, Eric, the opposite. So
because Oh, what we've been speculating in terms of the formation of these rays or particles, which still has to be determined. Likewise, that either there's a back bombardment against the electrode, which is causing a actual observable and tangible thermal heating of the electrode. That could be subsequently also producing the rays, or the rays producing a back bombardment. That still needs to be determined specifically. That's why a lot of this is still up in the air, because the detection of these rays and their effects are rather peculiar. The original intention that Tesla developed for these rays were to produce so-called Röntgen rays, or which we would call nowadays X-rays. But on the other hand, which is quite interesting, is that through rigorous measurements and development, that the rays are not characteristic in any way of Röntgen rays, other than being able to project what Tesla referred to as shadowgraphs or radiographs. That is probably the only inherent characteristic. Other than that, they behave drastically different. They seem to behave, and I'll be fairly general with this, they behave in an electrostatic nature. But as far as the actual generation of these rays, that's still being investigated quite intensely at the present.
Well, thank you. Thank you.
Yeah, I just came on. I'm Barry Green, and I live in Las Vegas. I have a multi-wave oscillator that was designed for me in 1975, and it was the Lakowski Tesla machine that now does not work. And I'm desperately trying to find someone that could help me put it back together. And I was just wondering if there's anyone in this group that's anywhere close to Las Vegas that I might be able to contact.
I guess not.
It's hard saying without knowing any details or size or schematics or any specs of the device originally, whether it's,
Right.
swapping a fuse, fixing a wire, or whether it's, redesigning a transformer or something. I guess you'd need to know a lot more about the system before even deciding to look closer at it.
Yeah, this one is just a little unit that is fits in a briefcase.
Oh, that's the old Bob Beck machine.
Yes. And I was just wondering if there was anyone here that may be familiar with that would like to try to fix it for me.
Well, I'm 250 miles away from Las Vegas. I suppose under the proper circumstances, I could look at it. But in general, it's a no visitors allowed location.
Yeah. Well,
Yep.
do you have, I know at one time you were coming to Tonopah. Do you still do that on occasion?
Yeah.
Because I could meet you there if we could set up an appointment.
Yeah, but like I say, that's a no visitors location. So there'd have to be, some kind of background check before you were allowed in the building.
Okay, well, no, we could do that. But no, I'm an architect in Las Vegas, and back in the early 1900s, you came to my mining claim here in Las Vegas, if you remember that.
Yeah, I had constructed this particular Corolla body there in Las Vegas around the time of the so-called Y2K. And then before that, the guy that had custody of the Integratron, he moved to Las Vegas. I spent a lot of time there in the late 80s. So our paths could have crossed.
Mhm.
Is that what you're saying? They did?
No, I had a mining claim and just south of Las Vegas, and we had 5 tunnels, and you came out and worked with me with the tunnels, and the power company had high voltage lines going
Well, somebody I think might have been using my name. I don't have a recollection of that, but I'm not saying it didn't happen.
Yeah.
I don't know, but I have a pretty good photographic memory of any type of power company stuff I come in contact with. I don't remember that happening.
Okay, then what would be the process for me to be evaluated or whatever it would take?
Well, the first step, you're going to have to write me a letter, and then
Okay.
then we'll take it from there.
Okay,
And Barry, if you want, if you can drop a little schematic and send me some pictures, I can't promise anything, but if you email that to me at the, my eMedia Press email.
Yeah.
Well,
actually,
I
I could
can
take
always-
photographs of it and send you photographs.
send me some pictures.
Okay. Good enough, because no, the man that built it for me passed away about 10 years ago.
Okay.
And I don't know of anyone, and I've talked to several people, and no one is familiar with it.
Okay. Yeah, just send me some pictures, and then on ericpdollard.com in the left column, scroll down and you'll see an address to a PO Box 992 in Tonopah.
Okay.
And that's where you can write Eric a letter.
Okay.
Okay.
All right. Good enough.
Okay.
Thank you very much.
Okay. Thanks, Barry. Okay, I'm gonna grab this phone from Eric. We'll kind of walk around, do a little tour of what we've been working on, and then Adrian will fire up his machine, and we'll show the golden ratio discharge. And again, it's kind of like what you would have seen at the conference, but he's done some modifications on it, and that's going to be integrated into some of what we're doing on the radio frequency bay to put those together. And that's the low hanging fruit for us to be able to have a high power demonstration at the conference, because we don't have time this episode to complete all the radio frequency stuff, but at least the audio bay is done. So Eric, if you want to bring that phone out here. Let's see. Eric's taking a break real quick. So would you want to maybe explain kind of what's going on here on the, so this you've probably seen pictures of over the years. It's finally working. The only thing missing is this grid control unit, which is kind of a preamp, which will take
so this has a pair of 1625 tubes in there. It's designed to take the outputs from the Hewlett-Packard oscillator, or to take that from some other kind of exciter unit and amplify it for the power amplifier stage. So at the moment, this should be capable of giving up about 50 watts of power. We had some problem with the tubes here. We had new old stock, but they weren't actually performing very well. So Eric was getting about 21 watts or so out of the system, which is enough for our test here, but it's not really enough to put it back in the rack. Eric, I was just saying about what we were getting here. You want to carry on that piece?
Yeah, these tubes are, we thought we got them from a reputable supply, and they're all flat. And the China Reich tube sockets are, those things are horrible. So one, they're all like real tight. You have to force the tube in, but then apparently some of the contacts are loose, and so the filaments are going dark, and so I got to tackle that. But otherwise, with the phone, can you kind of get into the architecture? As you can see, this thing was took a little thinking to put together to get it all to fit in and what have you, and get it to fit in the rack. And so I'm going to take the front panel, and it's fully metered. Various tube electrodes, input power, and all that kind of stuff. So right now I'm working on the old Navy World War II medium frequency. It's like a little transmitter, power oscillator. That's the antenna voltage right there, the neon lamp. And this is for driving the Colorado Springs coil, which operate in the AM broadcast band, I think 850 kilocycles. So that's why I'm working on this. And so that's basically what's going on here in this bench. So that's the audio bay. You want to go through what we had to go through to get the transformer?
Sure.
Yeah.
Sure. Aaron, if you come and have a look at the bottom here. So,
and you're just a second. Hey, Griffin or Hakasays, can you still hear this? Okay.
Oh yeah, you're good.
Okay.
Okay, so at the bottom here, we have the large modulation transformer.
Let me grab a flashlight over here.
So at the bottom here, we have this large modulation transformer. This is the final output from the audio bay. And when we were, so that it's arranged, this is arranged in a push-pull, the power amplifier. So it means that the high voltage, which comes from this unit here. So here we have the high voltage transformer. That's nominally 2400 volts.
You can turn the switch on and make this work, right?
I could connect it up and we could turn it on, yeah. So then we have the bridge rectifier, we have a choke, we have a load here as well. So this actually, this is connected to the power amplifier, which we'll look at in a moment, via the modulation transformer center tap. So in other words, the high voltage passes, or the high voltage DC passes through the modulation transformer and then is fed to each of the plates on the power amplifier. Now, that was where we thought that the problem was, because we have the high voltage feeding through the modulation transformer, and we were seeing a ticking on the scope, a little, I mean, obviously we can't see from the front. Then we thought, well, that looks like it could be a bad winding in the transformer, because we had everything else disconnected. But it turned out, I mean, if you come down here, Aaron, have a look. It turned out to be at the back here. We have this divider board, which is part of the high impedance input to the scope. And in actual fact, one of these resistors and one of these capacitors were actually a little bit too close to each other between the two segments of the divider. And it was there that it was ticking. But of course, we only discovered that once we got the transformer out. And you can see how compact and how tightly this is all in here. You have to take the panels off the front. You have to take the dummy load off. Then the transformer comes out the front with all the wiring and everything like that. So if we have a look at the power amplifier here, if you come and have a look, Aaron. So this is a pair of 810A tubes. Normally they're what, 2400 volts?
Normally, they're normally in an AM transmitter, they're normally operated at about 1500.
Okay.
But if you really want to crank, they're good all the way up to 2750.
2750,
So
okay.
I had intended them to operate on 2400 volts. That's about what we got when we turned it on.
I can probably, if I plug this in, we can power it up actually, Aaron. That's relatively easy to do. I should just be able to take these pieces. If I move it over here, let me put the HT on. And if I that's enough, yes, that's enough. We don't need the other one because we're not using the variac anymore. So we just need the one. So if you want to come down the front. So just to go over, we've got the oscilloscope. We'll turn that on, let that warm up. That's a Hewlett-Packard oscilloscope. It's from the 1960s, late 60s, early 70s era. Very good, very reliable. That's a tube supply. Then we got the power amplifier below that. We'll turn it on in a minute. This is the panels which Eric was showing you. So on the bench, you've got the exciter unit, which amplifies the audio oscillator into the power amplifier, or for that matter, any other thing that you want to attach. That goes in that bay here. And then we have a patch board, which Eric has designed, but needs to be constructed. So we can patch various things in. I mean, you take inputs from other amplifiers, from you know, you can connect a music source to this or some other kind of audio input, and that will get amplified through this stage into the power amplifier. Now, so far we've done the testing with the HP audio oscillator. We have a small matching transformer on the back, which changes the impedance. This is normally a 600 ohm output. down to 8 ohms, isn't it?
8 ohm, yeah.
The 8 ohms input for the power amplifier. And then down at the bottom here, this is the front panel that we have the high voltage supply that we showed you earlier behind. The dummy load set of light bulbs. And below that, behind this panel at the back here is the big modulation transformer we just showed you. So we got the scope up. Let's just get that positioned correctly. We'll turn on the audio oscillator as well. That should come on. And then we have, we'll turn on our main system. So the main switch in the middle just shows it ready. And we have a bias as well. And this is all interlocked. So the way Eric designed it is that you need to turn on everything in the right way. If something isn't biased correctly, then something else isn't going to work. So the first thing to do is turn on the filaments. That's now going to warm the tubes up. We'll just let those warm up a little bit. We can switch over the meter. So on this side, we're we're monitoring either the high voltage or we're monitoring the bias, which is applied to the grids. So we have a switch there that we can switch between what we're monitoring on here. So if you just come back, Aaron, to the meter, that's it. So at the moment we have got minus 60 volts on the grid. Nothing else is happening. We haven't even turned on the high voltage. We have the filament and bias as well. We can adjust that as well. So we can change the characteristics. But nominally, we just put it exactly where it should be according to the specification. Okay, so then we can turn on, we can get ready for our high voltage.
Your high voltage meter over here.
Yep. So we put it up back on the high voltage, back down to 0. We turn on, if you come back slightly down, we turn back the high voltage. We have a warning light for that, of course. And then down here, we have the final, this is the final safety switch for the high voltage. So it's basically that cuts the input line voltage directly to the transformer. So when we turn that on, it's going to put the line supply coming from the wall directly onto the primary of the high voltage transformer. So we lift, and that allows us basically to, if there are a problem, we can knock it off quickly, and that turns off the high voltage supply. So we put it on, and you want to watch here when I turn it on. I turn it on. Okay, so high voltage now, we have 2800 volts plate voltage. Plate current is currently set at around about 60 milliamps, and we could adjust that if we wanted to. So we can adjust the plate current down from about 50, actually it's almost 40, about 40, 45, and we can adjust all the way up to over 100, up to 120, but we're slightly overstressing the tubes. So we're going to set that back nominally around about 70.
So what happened, the meter's a little sticky. These things are from World War II Navy ships.
Jumped up and then went
and
down.
it got stuck.
Yeah. And then it went down. You saw that. And it went up to 2800 with the swing.
Wait a minute now. Why have we got 2800?
And then it went back. I also noticed that as well. And it went back to 2400. So
the meter's only 100 years old.
Yeah. Well, so it's all. So everything is now set. We look at the oscilloscope, where we see basically
acting a little goofy.
Well, that's also getting itself warmed up.
Yeah.
And we can adjust the frequency. So now I'm going to adjust the frequency on the oscillator, and up here we're getting direct audio amplification out. So I'm at about 1.3 kilocycles. I can go up further and further and further. I'd have to go up a range, even higher. It's 2 kilocycles. I go up onto the next range. Now, of course, we're up very high, so it's fallen off. Wind it down.
Get to this resonant point, you can see the dummy load light up.
That was about, if you look at the dummy load is now lit. Yeah, that was about the brightest we had it. So the reason that dummy load is not very bright, just have a look at this again, Aaron.
Can get it brighter. Right there.
About there, yeah. About there is the best. Now, obviously at the moment, we are taking the output from the audio oscillator. So we are not fully driving the tubes in the power amplifier. We are only driving them at about to about one quarter of their capability. But with the exciter unit that Eric still has on the bench, when we put that in, then we would light these very brightly.
Unfortunately, the oscilloscope is taking a squat on us, so that's something else that's going to have to be fixed.
Yes, it's reduced it some.
What's going on, but we'll figure that out.
It looks like it's reduced its time base. The time base, the X sweep is collapsed.
Could be this magnifier switch. It's dirty.
Yeah.
Yeah, I think that's what it is. There we go.
Yeah. Good.
Oh, those light bulbs are.
Yeah, they're nice and bright now.
Yeah, nice and warm looking in there.
So the purpose for this dummy load is directly over the output of the modulation transformer. So these bulbs soak up any transients, they soak up anything that could be a problem for the modulation transformer, because you do not want to damage that modulation transformer. And those can be plugged in when you're setting up an experiment for the first time. So you end up protecting the output of the audio bay by having those. If you want to run fully, when you're happy that everything is matched properly, you want to run full power, you could disconnect the dummy load here and run directly the output straight out of the output transformer. So it's basically a safety mechanism to have that in there. And that's it. And then, as Eric said last week, this is Navy specification. It's designed to sit here 24/7 every single day doing exactly this.
Okay.
We had it running. I thought we had it running for a good hour or two continuously, didn't we?
Yeah.
At the end of last week, everything sits in nominally in the middle of where it should be. Just take that down a little bit. Pushing quite a high plate current.
Okay.
And this is essentially now a completed and operative audio bay. Like I said, we've only got the last exciter unit and the patch board to get in, but otherwise it is fully working.
We'll talk a little on the RF stuff, and then we can move over to the demo.
Yes, okay.
Okay.
I'll just turn up the high voltage here. No need to leave that on. I'll leave that lit up for the moment though. Okay, so the RF bay, we have that in a lot disassembled here. I mean, there are a lot of units in here that are in part build, but we've taken. We would have, if we want to do that, then I can put it in. Okay, so the only unit we still have plugged in here is the high voltage DC, and this is missing the transformer plate on the back here. We'll show you that in a minute. But this is basically two high voltage DC supplies. So essentially, it's two 2400 volts. So we have everything replicated twice here. So there'll be two transformers, 2400 volts each. When those are combined in series, then you end up with 4800 volts. So 4800 volts out. That's configured by this patch board. On the front here, you can run in, Eric designed this to run in series or parallel operation, depending on the experiment. And largely, this is a large collection of chokes, high voltage capacitor. We have the bridge rectifier. We have the high voltage bridge rectifier. Can you get in there, Aaron? Just into that region there. You can see that there are basically a bridge rectifier. Those are 20 kilovolt, 2 amp semiconductor rectifiers, 4 of them each in a bridge rectifier arrangement. Then you have your load, your power load resistors. These 100-watt ohmites, 3 of them in series. That makes a 45,000 ohm load on there. That's nice to stabilize the output of the rectifiers. There are various chokes here as well, and it is designed, so it's designed to basically be a high voltage AM modulated supply. So it can run CW, or it can also take the input from the audio bay, and that gets modulated directly onto the high voltage DC, which then supplies various other stages, all the way up to what will be the RF. If you just put the camera under here, then you'll see this is the RF power amplifier. I mean, this is really just a bare design at the moment. It has the tube base. If I take that off, you can see, Aaron, there's the tube bases in there. There are the meters in there. Some of the metal work is done. But this still has a full design to do, and then behind that you've got the exciter unit. That is something that Eric. I mean, that is a masterpiece in itself. I mean, Eric designed essentially a Collins, a replacement for the Collins. And if you just look inside of that, if you see some of the complexity and the metal work and the detail and how the tube bases are mounted. I mean, people don't make this anymore. I mean, people don't know how to make this anymore. So, you know, this kind of design, you know, you are really looking at a lifetime of Eric's knowledge to basically even to put a design like that together. I mean, imagine the wiring and everything that goes into actually building this unit. So this is a replacement for the Collins, and goes in directly into the RF bay. Eric, you've also got another panel down here for the RF bay. You want to just show that one?
So that's the front panel of the rectifier and its control, the medium voltage rectifier for the filament transformers, and this is the back side of it separated. So there wasn't a lot of room left over, so I have to sandwich everything in the little space in between the two, which is going to be a bit of a challenge, but it'll be possible. And then that goes in. That's the next major panel up in the RF bay. Then the Collins goes in here, and then the grid control unit for the power amplifier itself, and then this will be the output tuning unit to match the power amplifier to the Tesla transformer.
And then if you just that's the Collins Eric's talking about that we've been using for the flame speaker and cosmic induction generator with this.
And if you just look on here, Aaron, so we were talking about the high voltage transformers. This is the high voltage transformer plate that will basically go into the bottom of the RF bay. This is a pair of General Electric JVM2s. They basically put out nominally 2400 volts each. When they are connected in series, they're quite bulky. So I mean, this is about 12 inches by about 10 inches, about 10 inches wide, and you know they weigh at least, I don't know, 15 kilograms each. I don't know what that is in pounds, but
they're about 30 pounds.
About 30, 35 pounds.
Okay, yeah. So this is, I mean, again, this is the kind of high voltage installation which is designed to run 24/7 all day long with this kind of very robust engineering. And it's this unit plus the one that we showed you in the bottom here. That is our priority to get working, because this will form the high voltage supply for the hybrid unit. So what we're planning to do here, Aaron, if you just look up here, so here, I mean, at the moment we just have a piece of wood there, but we will have a shelf in here, and then we will put the 3500 ZG generator unit that I use. We'll show you that in just a moment. That I use for the golden ratio discharge as an AM Innovations generator that I used at the conference last year. But since it is a fully developed RF generator already, we can use it as a hybrid unit prior to the other units being ready. We will drive it using this high voltage supply. So maybe if we take a look at that now, and if you come around this side, then you can see. So this is the AM Innovations RF generator for the golden ratio discharge. It was designed as a flexible unit. It can be driven as a power oscillator, also as a linear amplifier, and also as a push-pull pair of tubes. It has, and if you look inside for a moment, there are 3 stages. I mean, there's the output tuning stage here. So really, that is very similar to what the RF bay will have, but just on a smaller scale. So we have the vacuum tuning capacitor there. That's nominally a 4 kilovolts, 20 to 1200 picofarads. Then we have a pair of 3 500 ZG power tubes in here. This will also take a pair of 4 250s tetrodes, or the 4 1000 tetrode. Also the Amperex tubes. That's like the 4400, yes. Sorry, the 4400 tube. It won't take the 41000, it's the 4400. So it was designed for a very wide range of power triodes and tetrodes. In this section, basically, we have a HT inverter. We're not actually using this HT inverter in this setup. This is for other types of experiments, particularly electrostatic charging experiments. Underneath that, we have a toroidal transformer that provides the filament and all the other electrics that are needed. We have a discharge system in the back here, which uses the pair of vacuum. If you look down into there, you see a pair of vacuum relays in the back there with some power resistors, which form safe discharge of any electrostatic device that may be charged by the output. So, and all the necessary controls on the front, where the grid current, plate current, filaments, and high tension, and necessary tuning and adjustment of those things from the front. Then we have the AM Innovations high tension unit. This was an additional high tension unit I did for the golden ratio discharge, because it needs a source of about 4 kilovolts at about 2 kilowatts. You can see inside here. It's a very compact unit, this. Both of these were designed to be easily brought from the UK for the conference. But essentially, basically, you have a pair of high voltage transformers. You have a level shifter, which is a high power capacitive network that will basically shift the output of the transformers to a positive. This could be rectified. In this case, I'm using it as a level shifter, but I mean, that can also be used as a rectifier as well if you wanted to convert this unit to giving a DC output. It's SCR controlled. So rather than having a variac or something like that, you can control the power directly through a silicon control rectifier. That gives nice power control to the transformers. Now, what I modified here, Aaron was talking about some modifications. This is nominally a 4 kilovolt supply, but I put the 2 transformers here in series to be connected in series. Because I'm going to be using a different tube device for ESTC. This device will be powering, will be the output power unit of the hybrid RF bay that we're going to be building. And I will have a different unit here with a GU5B tube, and there will be another separate tuning unit. So this unit will be replaced for the conference with 2 smaller units here. One of those with to supply the GU5B, which is a Russian power triad, and then a tuning unit, which will have the coil, and the coil will move to a vertical position. So in other words, I won't be using the coil down in the horizontal. The reason I had this horizontal before is because this coil system can be slid. Last year, I was also not only giving a demonstration of the golden ratio discharge, but I was doing the vector network analysis in detail and using this coil in order to show how to do vector network analysis. So these two can slide against each other. If you just take a look here, you see this coil can be slid in and out, which allows me then during the demonstration, I could show how the vector network analysis worked. It also has another possibility where you can put a double-ended coil on here. So in other words, you can put the half wave arrangement. This is the quarter wave setup, but I have another coil like this back in the UK, exactly the same, that goes on the other side. Then the primary and the pickup are in the middle, and you operate in a fully balanced half wave scenario. That's also something else that needs to be demonstrated and presented that we'll do in due course. So at the moment, this is just set up for doing the similar demonstration I did at the conference. I can just run it and you can get the output. And the important thing about the golden ratio discharge experiment is what we were saying. So in other words, we're still working on that, how to get to probe the fundamental underlying natural principle and order in electricity, of which the golden ratio discharge is an example of one of those types of natural processes. And to do that, this entire system is driving this coil at the parallel mode. So it's what we discussed. This is a high output impedance, high input impedance to the coil for the parallel mode. The system is designed to transfer a lot of power to the coil as it needs it, as it self-oscillates. So overall, we're running this as a Class C Armstrong oscillator, power oscillator, up to about 2.5 kilowatts for relatively short periods of time. This is an experimental system for a lab. It's not designed like the audio and the RF bay. It's not designed to be running 24/7 all of the time. So you can put a lot of peak power up to about 2.5 kilowatts, but you can't run it at that level for a long periods of time. You have to let the transformers cool down. You have to let the tubes cool down. So that's also the difference in this type of benchtop experimental equipment and what we showed you with the audio bay and the RF bay. So we'll just make sure that we're turned on. Just check. Let me put this back on the back for the cooling. Transformers do the cooling when you're running, and it pulls in air from the back and puts it out from the front. It is kind of better if we turn the lights off.
Okay.
If someone see if I can just get the lights up there, it gives a better result. You sure you want all that stuff next to the coil when you fire it up? I will remove that so I can keep it. Okay, so we just start by.
It's by both doors.
Okay, so we just start by striking the discharge.
We played. I don't know why those lights are on.
They don't make any difference over here. Yeah, they won't. They'll be all right. Okay, so there we just got the discharge going. Very small. Just let the tube settle in for a moment. Start the oscillation. This is oscillating at around about 2.7 megacycles. That is also important. Frequency has to be relatively high also to get the golden ratio discharge. So we go up in power. That discharge is just a couple of hundred watts. Go up to the side. Just over a kilowatt.
It's a switch by the door in Troy's room.
About 200 milliamps. Yeah. 2 kilowatts, 1.95 kilowatts. If you use the black, I do my flip up here, you can get the black wall behind. That's 300. And just on a very, the sound you could hear coming from that modulator with the 60 hertz line cycle. You could hear that type in the background. Tune is good, not crackling, smooth. Just justifying the tuning and the bit bias to the pitch, that's stable. Sometimes when you hear the crackling, if I detune it slightly, you can hear now the tune's going to have a problem. That crackling you hear is where they're oscillating, and they stop oscillating, and they start oscillating again. So that's running stably at 2 kilowatts. Single transformer, not using 2 transformers, just a single transformer with a level shifter. So normally around about 4 kilowatts being applied to the primary circuit. Want to get it a bit closer, Aaron?
Zooming in.
Yeah. So that's max right now. That's max for the single transformer. When I have the G5P, I'll put both transformers on, and then it will go up to almost double the size. So that's as much as these tubes can take. You know, if you try to take them over 4.5 kilovolts, they'll just get half over in the tube. They do. And a nice healthy glow. We'll have a look around here. Getting a nice healthy glow off the tube slates.
Smell it.
Yeah,
You smell that metal melting.
yeah, maximum. All right, I'm just going to give it a pause. So I wouldn't run this for a long period of time.
Got some hot plastic going somewhere too.
Oh, there'll be somewhere on here.
High voltage off.
Yeah. Here,
Here's the current.
here, yeah. Here it will be warm on the primary. It's pushing quite a lot. I mean, it's pushing 2 kilowatts of power in there.
Okay.
With your reactive power, you're probably running about 20 kilowatts.
Probably, yeah. Reaction power.
Well, it's a tank circuit, it's things cranking hard.
Okay.
Particularly with that few number of turns at that frequency.
Yeah. Well, you have to. The turns can only be a relatively small number for that frequency.
Right.
Which is just.
So here's the brief demo there.
Change the coupling. Yeah. It's going to adjust slightly. That optical there. Right to the course later. No point. There's no hot plastic. I'll let it cool down now.
All right.
You can only run for short periods of time. Yeah. Because I mean, from a very tight, it's pushing a lot of power for a very tight, everything very tight and small.
Okay. Well, I'm going to get back to the laptop and then.
Yeah. Okay.
Okay. So, anybody have any final questions before we end the call? And I guess we could schedule for maybe 3 weeks from now.
Yeah.
Do it again.
Typical.
So 15th. What is that? May 6th. Would that work?
I might be
Yeah.
gone by then.
Yeah. You can do it from Tonopah.
Yeah, once I'm not in between.
Okay. Well, so far we'll plan on maybe May 6th. Anybody have any questions or anything you want to pitch in Griffin, Hakasays, or Adrian? So,
I think that's everything from
Okay.
from my side, from our side, I think.
okay, so I think everybody has the websites, and again, there's about 27 tickets left for the conference, July 5th through 9th. EnergyScienceConference.com, and then of course all the books, videos, that's all on emediapress.com. And anything anybody is willing to pitch in to help support EPD Laboratories Inc. It's ericpdollar.com, and if you go /donate, that's a shortcut right to the all the donate info, either by through the mail or by PayPal. And I think yeah, May 6th we'll do the next call. Victor, just stay in touch with me, not next week, but maybe early the week after, and then we can have you come over to the shop, and then I think that's pretty much about it. So anything else, Griffin?
No, well, I guess we could probably slightly allude to some possible plans in Tonopah during possibly the mid to later half of May.
Yeah, during May, there's going to be a few of the guys going down to Eric's shop, and then do you want to mention real quick what you're going to be working on down there, that hopefully you guys will be able to do some live video while you're down there in one of these calls?
Justin and I are going to finish the seismic sensing antenna system and our radio relay link. So this will be episode 2. That's all contingent. There's going to be enough money. I don't know yet. I hope there is. I'd be rather disappointed if there isn't. And at that time, Griffin and all are going to come, and they're going to finish the telluric test platform, which grounds to the tank, water-filled underground tank grounding electrode, which has spectacular performance. And then Griffin has completed the Alexanderson coil, and then the test oscillator, Navy test oscillator, I'm working on now, will have to be shipped down there. And then at that point, we're going to do a demonstration of the Alexanderson coil and some other experiments. And let's have to see, what pops up other than that.
Okay, and I'll get this video on YouTube for reference. I don't know, maybe next week, something like that. There's a lot going on, so I'll do it when I can. So May 6th for the next one. Then also on, if y'all haven't seen it, and we're just wrapping up, we'll be done in here in just a minute. I'm going to show a, let's see, emediapress.com. Let me do a screen share real quick, then we'll go ahead and end the call. So let's see, on the blog on emediapress.com, I just posted this Brother Sanchez TV. There's a 4.5-hour interview, mostly with Eric and Adrian, and you can come here to see it. And they go into a whole lot of different, whole lot of stuff. Eric went on for about a little over 2 hours, and then Adrian was on there, and we did a couple demos, the golden ratio demo, and did the flame speaker thing, and the crazy cosmic tube and that kind of stuff. And there's a little bit of flat earth conversation that got a couple people lit up. But anyway, that's on there for 4.5 hours. It's pretty entertaining. And we have an open invitation to go on that show, because there's a lot of exposure. There's over 120 something thousand subscribers on there. So yeah, it's introducing a lot of people who wouldn't normally know about this kind of stuff. It was a good intro to them. And so I guess until next time, thanks everybody for being on the call, and we will see you all next time.
Right. Thank you, Aaron.
Okay, thanks everybody. See ya.
Thank you.
Take care.
Bye-bye.
Thank you. Thank you.